There are two real big benefits to understanding significant figures. The first one is significant figures shows us the precision of a measurement. We've talked about that in previous videos. But it also shows us how to round our answer. If everybody follows these steps everywhere in the whole wide world, then everybody gets to the same answer every time they're doing a calculation. And so here's my explanation. Scientists, engineers, and people all over the world use this concept so that they can get to the same answer. So they can also show the precision of the measurements that they used to get to their answer. Now, this is what we're going to cover in this video. I always get the question in class, how should I round my answer? What decimal place should I round the answer? Well, I can't answer that question because it's dependent upon the numbers that you use to calculate the answer. So significant figures is the only way to really answer this question in science and engineering. In the previous videos, which if you haven't watched them, I highly encourage so you know what's going on here. But I did cover this right here. You need to know how to count how many significant digits are in a number before you can actually do math with it and figure out how should I round that number. So look in the description, take a step back, go watch that video. But if you didn't, and if you're not planning to go back, it is up here on the screen. I would highly encourage you to write it down so that you have this information. You'll need it. I tell my students, you'll need this the rest of the year, and you will need this well beyond if you take any science or physics class after my chemistry class in high school. But these are the rules that we're going to use to count significant digits so that we can answer the question, how should I round my answer? Now, here's the thing. Anytime you see a box around something up on the screen, that's something that I have identified as a teacher that is super important information that my students and you need to know for the rest of the year, and oftentimes well beyond that, right? These are the important things that if you were looking back through your notes, you want to have some way to identify them as extra important. I put a box around them on my screen. My students often put a box around theirs. So there are two sets of rules for operations. The first one is for multiplying and dividing. When I'm multiplying and dividing, the answer that I write down is limited to the fewest number of significant figures in the problem. Now, as you write that down, if you're writing it down, just know that this isn't going to make really good sense until we start doing examples together. So if you just write it down, you have that information, we'll do some practice problems, then you'll be like, oh, okay, well, now I actually understand what that means. When I'm adding or subtracting, there's a different set of rules to figure out how I should round my answer. And then in this one, I'm not just looking at all the numbers in the problem. I'm rounding my answer to the same place value as the least precise number. Now what? Again, stick with me because when we go over the examples, we're going to clear that up. We're going to start here with multiplying and dividing. I think it's a little more clear. It's an easier place to start to understand this. So this is information that I just gave you, but I added a little bit here. If our answer is limited to the fewest number of significant figures in the problem, how do I get to that point? First thing we're going to do is count the number of significant figures in each part of the problem. I'll show you that. And then we'll determine how many significant figures we get to have in our answer. We're going to have to round our answer off. Well, we round it off using significant figures. Maybe I have an example problem here that says 34 grams divided by 10.1 milliliters. I've left the units off so that we can just focus on the actual number here and walk ourselves through it. That's what my calculator screen says. And there's a lot of digits there, and I can't leave those digits there because if I did, that would imply that I had really, really good devices measuring this. Like to be able to go down to that many places, but I didn't, right? These are fairly simple numbers. They're not that precise numbers. So this is actually not, we'll say it's not true. We have to be careful about that. So the question becomes, how do I round it? Well, let's walk through this step by step. How many significant figures are in 34 grams? Well, each one of those is a significant figure because, well, non-zero numbers. How many significant figures in 10.1? There are 3. Now let me show them to you. There's one, and this 0 is called a trapped 0. That is a significant figure. So we have 3 significant figures in that problem. How many significant figures then do I get to have in my final answer? Well, I'm limited to the one with the fewest number of significant figures. And in this case, this one has 2, this one has 3, so I get to have 2 in my answer. Well, then my answer would be this number rounded off to two significant figures. How do we do that? There's one significant figure. There's two significant figures. I always look at the next number, and we're going to go with the rule that if it's 5 or higher, we'll round the number up in front of it. If it's 4 or lower, we won't worry about rounding this up. Now, fair warning, there are some more rules with significant digits that tell you how to round. But I have found, especially in chemistry and introductory chemistry, we don't need to worry about that. Let's revert back to what we know and just focus in on getting the correct number of significant figures. And then if you move on in engineering and or math and you're using big data sets, you'll learn about a few more rules that we're not going to cover here because they're just not necessary. So if I round that up, my final answer is going to be 3.4. And of course, if I have the units on there, grams per milliliter, we're not going to spend too much time focusing on the units because we're just trying to learn how to do this for now. Let's try another one. 1.20 centimeters times 10.11 centimeters. If I plug that into my calculator, I'm going to get a number looking something like 12.132, and that would be centimeters squared if I'm keeping track here. And that means I need to look at each part of this problem and decide, well, what should I be rounding my answer to, right? That's the whole point of this part of significant figures. How many significant digits here? Well, there's 1, 2. The zeros are the ones we always need to think about. Now, this is what's called a trailing zero because it comes after the last non-zero number. This is a trailing zero. Trailing zeros are significant if there's a decimal somewhere in the number. So this number has 3 significant digits. Again, if you're struggling with those rules and you're not really understanding what I'm talking about, go back a video where I teach you how to count, which is what I'm doing here, because if you can't do any of this if you can't count significant digits. Here, the ones are definitely significant figure. The ones are definitely significant figures. The zero is the one we have to worry about, but this is what's called a trap zero because it's in between two non-zero numbers, which means there are a total of 4 significant figures here. We look for the one with the least number of significant figures, and it looks like this one has fewer significant figures, and it has 3 significant figures. So how many do I get to have in my answer? 3, which means I look up here at my answer and I say, okay, there's one significant figure. There's a significant figure. Here's the third one. 1, 2, and 3. And then I always look at the number after that and decide, is that 5 or higher? Should I be rounding this number up? In this case, it is below 5. It's a 4 or lower. So I don't round it up, which means my final answer is 12.1 square centimeters. We good? Our next example has scientific notation in it, and that was one of the rules we went over before. How do we deal with scientific notation in a problem? So let me show you how to deal with this, and I'm going to teach you something else about using the calculator that is going to be the most valuable thing you've learned about your calculator, if you don't already know it, to ensure that you get all the questions correct in chemistry class, and oftentimes in physics class, at least every time you're running into scientific notation. Now, I'm telling you, this is going to be hugely beneficial to you. Remember, the number was 2.61 times 10 to the 6th. So don't use the times 10 and find the little caret or the hat or whatever they've taught you. The most important number you can know for right now, and really for chemistry as you work through beginning chemistry, is this number right here, EE. That EE stands for enter exponent. Okay? A little e shows up on the screen because now it's saying, okay, wait, you want to do scientific notation. Mr. Beals, that sounds really good. So we have 2.61 times 10 to the e right there means times 10 to the, and our number, when I come over here and look at it, was 6. On the screen right now, you see the best way to put in your calculator the number 2.61 times 10 to the 6th. Because we don't need parentheses, we don't need to remember where to put the little hat or the little caret or any of the fancy stuff. I'm now telling the calculator I'm using scientific notation. I want you to give me the correct answer by doing the correct order of operations, and it will, because that's what they do. So now the problem was 2.61 times 10 to the 6th divided by 0.0034 equals, here we go, this big crazy long number. Now I'm going to switch back over. Here we go. This needs to be rounded off because there isn't a single number up here that is so precise that we can have that many digits in our answer. So we go right back to our rules, which are posted right above, and we say, okay, how many significant figures in that part of the problem? And if you followed through the rules, we only count the ones that are in front of the times 10 to the, and that's because, well, those are all zeros. They're trailing zeros, and trailing zeros are not significant unless there's a decimal in the number, which means this has 3 significant digits. Oh, the other part of the problem is 0.0034. These two are significant digits, and we look at the zeros. Those zeros are called leading zeros. Leading zeros are never significant, no matter what, which means they matter. They're important. We don't get rid of them. They're just not counted with significant digits, so this number has 2. If I go back to the rules up here, then how many significant digits do I get to have in my answer? Well, hopefully you're getting this figured out by now. You get to have 2. So I take this whole great big huge number and I round it off to 2 significant digits. Let's do that. We look at the first two. We have a 7. Okay, so we're going to take that 7. And we have a 6. So that's 2 significant digits. But I look right here and the next number back is 5 or greater. 7 is greater than a 5. So that means that would cause this number to round up. So I would have 7, 7. And then I would have 1, 2, 3, 4, 5, 6, 7 zeros. So 1, 2, 3, 4, 5, 6, 7 zeros. This is joules per second. And if you follow along on my videos as we move through here, you'll find out why we're learning about joules per second. It'll be useful down the road. And this is 770 million joules per second. If I'm going to rewrite this in scientific notation, which becomes really useful down the road, I would have 7.7, and that means I had the decimal moved 1, 2, I'll go this way, 1, 2, 3, 4, 5, 6, 7, 8, 7.7 times 10 to the 8th joules per second if I'm doing this in scientific notation. Look at us go. We're doing well. Well, hopefully you're feeling good about multiplication and division, and you understand those rules and how they teach us how we should round off our answer. The next step is, well, what if we run into a problem where we have addition and subtraction? These are the same rules that you wrote down earlier. I haven't added anything here because I think this one warrants some verbal explanation to get you through it. So we put that into our calculator, which I did over here, and it shows on the screen 533.536, and this would be grams. So the question becomes, how should I round my answer? If you're following along, well, we've got to look up there, but notice this one's different. So which number is less precise? The easiest thing to do is to first look and see if there's a decimal in the numbers. If there is, then we can just look at the precision after the decimal. We can look at how many significant digits are there after the decimal. Over here, there are 1, 2, 3 significant digits after the decimal, which means that 0 is in the tenths, hundredths, thousandths place. Okay, then this one over here, it's got 3 significant digits after the decimal, which means that 6 is in the tenths, hundredths, thousandths place. So which number is less precise? Well, we have to be careful with this one because it turns out they have the same precision. They both have places. They both go down to the thousandth place, or 3 places after the decimal. So what's the place value of the last digit in 334.540? We just answered that. It's the thousandths. Good. And in the other number, the place value of the last digit right here is in the thousandths, which means in my answer, I should round to which place value? Well, there we go, to the thousandths. Right? If I look at the answer that was on my calculator, turns out that answer does go down to the thousandths place, which means my answer is the same thing I wrote up here. 533.536 grams is the correct answer. Let's try another one with subtraction this time. We're going to follow the same rules as the one before. And if I put this into my calculator, I end up with the following number. I'd encourage you, get out your calculator, put these numbers in, follow along, pause the video, see what you get, and then move along. It's way better if you participate in this instead of just listening to me the whole time. I'm looking at my calculator over here, so I just plugged it in, and I got 0.1182. Now, technically, I'm showing a 0 out front there because that's a placeholder. It's not a significant digit, but it's a placeholder. So I have 0.1182. Forgive the poor handwriting. Which number is less precise or least precise? Over here, we have two significant digits. This one's not a significant digit. It's a leading 0. But I'm looking after the decimal anyway because it's addition and subtraction. And I don't much care about the ones up here for addition and subtraction if the numbers all have decimal places because I'm looking at precision. So here, we've got significant digits in the tenths and hundredths place. Over here, we have significant digits in the tenths, hundredths, thousandths, 10,000ths, 100,000ths. This one's really precise. This is a significant digit because it's a trailing 0 and there's a decimal in the number. So we have, but remember, we're not really looking for the one that has the most precision. We're always looking for the one with the least precision because that limits our answer. So which number is less precise? Right here, the 0.18 is less precise. What's the place value of the last digit in that? We said tenths, that's tenths, and that's hundredths. So I'm going to write hundredths. For the case of the other one, since we talked about it, we have tenths, hundredths, thousandths, 10,000ths, 100,000ths. How do I write that nicely? 100,000. Just take my word for it. That says 100,000ths. Basically, my answer should go to what place value? It should go to the one that was less precise, and it should go to the hundredths place. So that means we're going to have to round our answer up here to the tenths, the hundredths. We always look at the number after that and see if it's 5 or greater. In this case, it is because it's an 8, which means that would cause us to round this number up, and our final answer then is going to be, I'll put that 0 as a placeholder out front, 0.12 meters. Look, we're getting pretty good, right? In multiplication and division, we know how to round our answer. Addition, subtraction, we're figuring out how to round our answer. So let's try one more and see if that's enough. Here's what I would highly encourage you to do. Pause the video, type this one in, work through it, see what you get for the final answer, and come back here and check. Did you pause it? If you didn't, well, I'm going to work through it anyway. So hopefully you're still learning either way. I think a lot of us could do this right in our head. I'm double checking with our calculator over here, and it does say 108.02. I'm going to put the milliliters on there because it's important to have the units. And then you need to think your way through this. What's the next step? The next step is to figure out, well, which number is less precise? It looks like this is less precise because there's nothing. There is no decimal and there's nothing after the decimal. If this was a really precise measurement, it would have a decimal and then places after the decimal, much like this number. But it doesn't place. This is the ones, the tens, the hundreds. Hundreds, not hundredths. And the other one, 2.02, if we're looking at the precision here, it has in the tenths, so that's after the decimal, and the hundredths after the decimal. So it has precision down to the hundredths. But we're not looking for the one that's the most precise. We're looking for the one that's least precise. That's this one. It has a significant digit in the ones place, which is a really, really weird way to say that we just need to round our number off to this place, the ones place, which means my answer is 108 milliliters, 108 milliliters. Here's a real world example of why this is important, why your measurements are important, and why being able to round with significant digits is important. These are two scales in my chemistry classroom, and I plopped the same penny on each of them. And to give you an example here, we're going to add the mass of this penny on this scale to the same penny when it's on this scale, which means we have 2.48 grams plus 2.4779 grams. It equals 4.9579 grams. But remember, we can't leave it that way. We just learned the process that when we have addition, we need to look at both parts of the problem and show that same precision in our answer. So over here, I'm going to look after the decimal first, and it does have numbers after the decimal. In fact, it goes to the to the tenths and then the hundredths place. So 2 places after the decimal. This one goes far further, 10 hundredths, thousandths, 10 thousandths, or 4 places past the decimal. We're looking for the least precise one over here, which has significant digits in the tenths, hundredths, which means my answer can have a value in the tenths, hundredths, and because of the 7 here, I need to round up. So my final answer would be 4.96 grams. That's the answer to number 1. Now here's the thing. Let's try something. We're going to calculate the mass of the 2 pennies using this value over here. All right, because this is more precise. So this will show you why the values that we use to get our answer determine how precise our answer is going to be. So we're just going to take the 2.4779 grams right here, plus, now if we had another penny, exact same, 2.4779 grams, that equals 4.9558 grams. Again, we always have to look and see how should we round our answer. Well, look, these are the same numbers. So if we count it up, we're looking for precision after the decimal. That's the easiest place to start. We can see we have tenths, hundredths, thousandths, 10 thousandths. Another way to think of that, after the decimal, we have 1, 2, 3, 4 places after the decimal. Same over here, 1, 2, 3, 4 places after the decimal. So guess what? My answer can go 4 places after the decimal. Let's write out this final answer then. It's 4.9558 grams. Now here's the thing. Let's compare these two. This one has been rounded off to 2 places after the decimal because one of our measurements wasn't very precise. This one is rounded off to the tenths, hundredths, thousandths, 10 thousandths, and it's showing that this is a really precise measurement. These numbers are not exactly the same because one of our measurements was made using a less precise scale. In chemistry, in science, in physics, in engineering, it's so important that we use as much precision as we possibly can because, as I mentioned in earlier videos, more significant digits is more better if you're talking about the amount of precision that your instrument has. And notice, this is technically, we'll call it a better measurement as long as we have good balances. I really hope that that helps demystify significant figures and how to round significant figures. If you have questions, if you have problems, feel free to put them down there in the comments. I really do check them. And then the community, as it starts to grow, people can help each other out and really help you and your classmates and other people across the world in the internet figure out how to use significant digits and then find out they're not as frustrating as maybe you thought they were. There is one more thing that I want to include with significant figures. I'm not including them in this video because some people don't need to worry about them. Now, if you're in my chemistry class, you would need to worry about them. So that's why I'm going to make one more small video to deal with non-measured numbers and exact numbers. And there's stuff popping up on the screen. Come over to Beals Science, bealsscience.com. Go to the Beals Science School YouTube and check out all the lessons I have to teach you science. And the real reason I do all of this is to convince you to keep on learning.